Welcome to lecture 10. So today we are going to start our third chapter in colloids and surface science. This chapter is all about the liquid gas and liquid-liquid interface. And mind you, this is the biggest chapter in this colloids and surface chemistry course because this chapter would involve surface interface, surface tension, contact angle, uh, phenomena at the curved surfaces, micelles, surfactants, self-assembly, uh, emulsions, etc. Alright, so we have a long way to go. So we would start from few very basic understanding or concepts. So whenever we talk about liquid gas and liquid-liquid interface, so that means if we change the gas as air, then we are talking about surface, because the definition of surface is the interface between liquid and air. And then when we talk about liquid-liquid interface, we should be talking about an interfacial tension. So therefore, whenever there is a surface or interface, we have surface or interfacial tension respectively. So therefore we begin with the definition of the surface tension, or it is also known as surface free energy. So this is defined as the work required to increase the surface area of the existing surface isothermally, means without changing the temperature, and reversibly, that means surface should not be destroyed, so it can be stretched or it can be compressed by 1 unit. So this is the definition. So work means energy, so this is the definition of surface tension or surface energy. So now let's take a look at once again the molecular source of the surface tension. As I have mentioned earlier, that suppose we have here air and we have a liquid here. So this is the interface between air or liquid, or simply the surface. So therefore, what happens that we have the molecule at the bulk. Okay, this is the liquid molecule at the bulk, and this is at the surface. So a dynamic process goes on even at the room temperature. So the dynamic process is that this molecule can come up to the surface and can get vaporized. And experiment says that in a most common liquid like water, the time that on an average a liquid molecule spends at the surface is about 10 raised to the power minus second. Okay, so now the thing is, if we have more surface tension, the liquid have less vapor pressure, and we have less surface tension, the liquid have more vapor pressure, because the tendency of the liquid molecule to overcome the attraction of the surface or the medium, and they can cross the barrier and move into the air in form of vapor, so it would create the vapor pressure. So now, as I have already told you, that the reason for origin of the surface tension is the unbalanced intermolecular force. So this when in the bulk, the molecule would face the intermolecular force of attraction from all direction. So the unbalanced force at the surface would tend to pull the surface molecule towards the bulk, and surface tends to contract, and that is the origin of surface energy or surface tension. So now let's take a look at the few different types of liquid in this case. So let's talk about the surface tension gamma of water. So I just writing here gamma W. Now what is the origin for gamma W? So origin for gamma W is the intermolecular force of attraction within the water molecule. And by now we already know that the main reason for the intermolecular forces is the van der Waals forces, and that is present in any liquid or any substances. So gamma W is equal to gamma W van der Waals plus there is some special case happening in water, that is the hydrogen bonding. So gamma W we can write H stands for the hydrogen bonding. So now if we talk about hexane, so gamma hexane, so this is a non-polar liquid. Okay, so for hexane you see we only have gamma W van der Waals because we don't have the hydrogen bonding. But obviously these van der Waals forces are weaker than gamma W, sorry, here it should be hexane. So this gamma hexane van der Waals should be less than the gamma water van der Waals, only because here in hexane the van der Waals forces are only dispersive, that basically it's a London dispersion force. But for water these van der Waals forces are actually a summation of London forces, Keeson forces and Debye forces. That means we also have the dipole-dipole and dipole-induced dipole interactions. And then if we talk about gamma mercury, Hg, it would be obviously gamma mercury van der Waals forces plus there is something, because we all know that the mercury has a very high surface tension, much higher than the water and the hexane. So what is the reason, what is the origin of that huge force or huge surface energy? The reason is mercury has once again has a very special situation happening within its atoms, that is metallic bonding. So there is a special kind of connectivity between mercury atoms, and so we call it the metallic bonding, and due to this we have this gamma mercury M. Okay, so now what we are talking about, it is the pure liquid. So in pure liquid these are the different types or varieties of the intermolecular forces of attraction may operate. So now let's change the scenario a little bit. So we move on from a air liquid interface, or in other words, let's move from surface to an interface where we have two different immiscible liquids. So we can think about an oil water interface. Okay, so let's see how would we can assess the interfacial tension between oil and water. So what we can think about, so let's go to a microscopic view at the oil water interface. So let me draw some molecules here. So, and I'm shading it. Okay, so shading means I wanted to say that these are my water molecule H2O, and then we have some unshaded molecules here, and these unshaded molecules are oil. Okay, now this part is actually the oil water interface. Okay, so now if we consider what are the forces that are operating at the oil water interface, so let's try to figure it out. Firstly, you see that the oil molecules the at the interface would experience the pull towards the bulk. So we have simply gamma oil here. Okay, so this gamma oil is something like this. It is the pure surface tension of the oil, okay, pulling towards the bulk. And then of course we have this gamma H2O, so or gamma W. So gamma W, once again, it is the pure surface tension of water. So it's the same force, by the same force the molecule at the interface is getting pulled towards the bulk. But now you see we have the interface of between two different substances, that is oil and water. So therefore what would happen, that these water molecules would feel a pull towards the oil medium, and this pull is mainly due to gamma van der Waals oil water. So we can write OW. All right. And also similar fashion, in similar fashion, the oil molecule would feel a pull towards the bulk water medium, and this is the by the action of the identical force with this one. So this is again gamma oil water van der Waals. Okay. So how we can summarize the net forces? Okay. So from a physical point of view or from mathematical point of view, we cannot deduce any physical formula for the net gamma oil water interface, but we have to take the help of an empirical formula. All right, and the empirical formula was given by Folks. So I'm going to erase this part of the board and I'm going to write that empirical formula, and let's try to see what are the interesting situations that can take place by studying that formula. Okay, so let's do it here. So I have written the Folks empirical formula over here. So it says that gamma oil interface, oil water interfacial tension. So that means here the oil water interfacial. So the tension, the net tension at the oil water interface is denoted as gamma oil water I. All right. So same thing is written here. So this is expressed as the summation of pure oil surface tension, that is gamma oil, plus pure water surface tension, that is gamma W, and obviously here the gamma oil is gamma van der Waals and gamma W is gamma van der Waals plus gamma hydrogen bonding, minus sign, because you see that here there are four forces, two are at the same side and two are at the opposite side. So all those are not at the connected by the summation term. So some are collective, means some are additive and some are subtractive. So therefore minus twice of the addition of these two forces, that is gamma oil water van der Waals, and means twice of gamma oil water van der Waals. So now at the next step, Folks proposed, or he showed, that this twice, that is how to find out this gamma oil water van der Waals. So it is the geometric mean of individually gamma oil van der Waals and gamma water van der Waals. So this expression over here is equal to whatever a gamma oil water interface is actually the Folks formula, and sometimes this helps us to find out several van der Waals interactions between two different immiscible mediums. That means van der Waals interactions at the interfaces of two different immiscible liquids. So how it can be done? Let's take an example. So here I have also written a chart. So this chart actually mentions the experimentally measured surface tension and interfacial tension of different liquids. So all these values are denoted is in the units of millinewton per meter. Okay. So let's first go with this water. It has surface tension, pure water surface tension 72.8, and it is nothing there because gamma IW means a liquid's interfacial tension when it interfaces with water. Okay. So next we have carbon tetrachloride. As you see, that it is 26.8 pure carbon tetrachloride surface tension, and when it interfaces with water, the interfacial tension increases, it gets 45.1. N-hexane is very low, 18.4, but when it interfaces with water, it increases 51.1. And marker, interestingly, very high. You see 485 millinewton per meter. It decreases at 375 when it interfaces with water. Okay. So now, in the given example, if I suppose take the oil medium as N-hexane, all right, then can you identify or calculate the value of the gamma N-hexane water van der Waals at the hexane water interface? Can you do that? Or in other words, what I'm trying to do is, suppose here, if I want to apply this thing over here, so N-hexanes, gamma IW is 51.1, so we can write here this is 51.1. all right, and this is equal to gamma 0, which is 72.8, plus gamma oil, not gamma 0, so that was the gamma oil. So gamma oil, which means N-hexane. So here we have N-hexane 18.4, okay, so this one, plus gamma water is 72.8, which is this one, minus twice of, now we have gamma oil van der Waals. Now you see this N-hexane's gamma S 18.4, it is nothing but the gamma hexane van der Waals, which is gamma oil van der Waals here. So we can write 18.4 over here multiplied by gamma water van der Waals. So we don't know this because it is the interfacial tension when water interfaces with N-hexane. Okay, so is equal to 51.8. So now can you figure out gamma water van der Waals at N-hexane and water interface? Okay, so can you figure it out? So you see, with this formula you can easily figure it out, and this type of small numerical problems I have seen appearing in GATE and especially in NET exams. Okay, so for solving such type of numerical problems, you must understand and should be able to apply this Stokes empirical formula. All right, so now we've got some understanding how the interfacial tension works. Okay, so for the time being, in the next section we would deviate a little bit from this interfacial tension, but remember, we will have to come back later because whenever we are talking about this interface between liquid gas or liquid liquid, the gamma term would always be there, so you will see that, and this interfacial tension would be again relevant when we come to talk about some wetting and contact angles, etc. All right, so for the time being, let's focus something at some phenomena that is happening at the liquid gas interface. So let's clean the board and start discussing that. So now let's talk about some physical phenomena that takes place at the liquid gas interface. So let's first start with a simple consideration that we have already discussed during the introductory lecture. That is, if we have smaller particles, then according to the colloids and interfacial sciences, the smaller particle would have enhanced surface energy, enhanced surface area, and that you would agree. That means I'm talking about the total surface area is to volume ratio be very high for the smaller particles. So we say the smaller particles have relatively higher or enhanced surface area. Now we all know that these I have already discussed that enhanced surface area means enhanced surface energy. All right, and there is no doubt about it. So now the thing is, if we have smaller colloidal particles and those particles have enhanced surface energy, so what implications it may have? Now this enhanced surface energy has two very important implications. If the particles are basically liquid, that means if these are liquid droplets, or if the particles are solid, like nanoparticles or something. So this enhanced surface energy due to enhanced surface area would give rise to an enhanced vapor pressure if the particles are in question are liquids. And if the particles are solid, the enhanced surface energy give rise to enhanced solubility. Okay, so there is an equation that comes from thermodynamics, a mathematical equation that relates this, how this enhanced surface energy is does affect the enhanced vapor pressure and enhanced solubility. So that equation is known as Kelvin equation. So it comes from thermodynamics and physics of surface. So this Kelvin equation actually describes the topic that is called the phenomena at the surface or surfaces. Now, the most general assumption that when we make that when we talk about some smaller particles, the general assumption that we take that these are spherical entities, that means spherical in shape, smaller particles, be it liquid or a solid. So whenever we have the smaller particle, means a spherical particle, the surface becomes, means a portion of the surface, if we talk about, it becomes a curved surface. So therefore, the Kelvin equation does describe the phenomena at the curved surfaces. All right. So that would be the topic of our current discussion, that phenomena at the curved surfaces. Now, before we proceed further to deduce the Kelvin equation, so we must get ourselves familiar with few basic thermodynamic equations. So see, when we talk about surface energy or we talk about surface tension, so surface tension is nothing but surface free energy. Okay, so that means this term free energy is very important. Now whenever we think about free energy, we think the Gibbs free energy, G. All right, so in thermodynamics, the behavior of or dependence of G with respect to temperature and pressure for a pure substance is given by VdP minus SdT. So this is always true for a pure substance. So that means this is not a chemical mixture, because for a chemical mixture, G also depends on the number of moles of the different species that are changing, but we are not talking about that. We're only talking about pure substance. For pure substance, dG is equal to VdP minus SdT. So now, the same equation, if we think about at constant temperature, all right, and we divide everything by the number of moles, say we have a pure substance of, n number of moles, so then, or at constant temperature, these parts become 0. So we can write dG divided by n is equal to VdP divided by n, where n is the number of moles for the pure substance. So and therefore, so this dg by n becomes d mu. All right, so this is the mu is also known as the chemical potential, and mathematically it can be defined, it is the change, infinitesimal change of the Gibbs free energy divided by the number of moles for a particular substance is equal to, it becomes V bar. So V bar is now becomes the molar volume, V bar dP. All right, now we have two different scenario, that for a finite change, if it's a gas, so for gas, and if we assume that the gas behaves ideally, then this becomes, then d mu is equal to, if we change the molar volume, RT divided by P dP, or then straight away we can take this as RT d ln P. All right, so therefore also we can write that for a finite change, delta mu is equal to RT ln pressure final divided by pressure initial, PF divided by PI. All right, so that is for gas. Now same thing for liquid, the finite change would become delta mu is equal to V bar multiplied by delta P. So delta P is just the change of pressure. Okay, so we have two different definition for delta mu. Okay, so once again, this is delta mu for liquid and this is delta mu for gas or vapor that behaves ideally, is equal to RT ln pressure final divided by pressure initial, and there is delta mu liquid is equal to molar volume multiplied by the delta P, that means the change in pressure, or in other words, okay, so we will take a look at, we would take a look at what is the delta P. So delta P would depend on the situation, okay, or the system that we are defining. So anyway, with this much of knowledge, we can now proceed to deduce the Kelvin equation. So let me clean the board and start deducing the Kelvin equation. So now we are going to derive the Kelvin equation. So for that, let's assume that there are two systems. So one at the left is a situation where we are very familiar of. So there is a liquid. We can think that it may be water or something else. And it's a closed container. So on top of it, we have the vapor of the liquid. So it has the vapor pressure. So that portion is full with the liquid vapor. And if you see what happens, that for a system like that, and obviously it is at equilibrium, so that means there is a equilibrium at equilibrium has achieved when the liquid molecule is going to vapor, becoming vapor, and vapor molecules are coming back to liquid. Okay, so it's a dynamic process and the equilibrium has been achieved. So where pressure of the vapor pressure is P0, that means pressure above the surface is P0 and the pressure just below the surface, okay, is also P0. So now what happens, that somehow we don't try to assess that what's the mechanism, but we only concentrate on the result, that somehow the surface of the liquid become convex, okay, becomes curved. So therefore obviously the vapor pressure would change. Also the pressure means here whatever P0 is there, at this situation we do not have the P0 on the outer surface or inner surface. So the new vapor pressure would be P, and we assume that the pressure just below the convex surface, so this is the convex surface now. So the pressure right below the convex surface is assumed to be P1, and once again the entire system was allowed to equilibrate. So that means when it's under equilibrium, the same thing happening, the liquid becoming vapor, vapor becoming liquid, and an equilibrium is there. All right. So now let's try to assess that what are the changes that has been made when we go from left to right. So first let's concentrate that what is the change of the chemical potential of the vapor. Okay, so that is delta mu vapor. Okay, so the delta mu vapor is nothing but the mu vapor, so final minus initial, so final is here, so that is mu vapor on the curved surface or above the curved surface here, which is at the pressure P, minus mu vapor here on the plane surface, which is at the pressure P0. All right. So therefore, now how we can relate these two? So therefore you see that if this is a finite change, and we can assume that this vapor behaves ideally, that's an assumption. So therefore we can straight away write that this change should be is equal to RT ln P, which is the final, divided by P0. And remember, this is the expression we already wrote just a while ago. All right, so this is the change in the delta mu vapor. So now let's try to assess what is the change in the delta mu liquid. All right, so the delta mu liquid is, once again, this is the mu liquid just below the convex surface, and which is at the pressure P1, minus mu liquid below the plane surface, and which is at the pressure P0. All right. And also from our earlier knowledge that the expressions that we have written a while ago, so this difference would be the molar volume multiplied by the pressure difference. Okay, so that means final minus initial, P1 minus P0, or in other words, this is equal to V bar delta P. So delta P is the pressure difference between the pressure below the convex surface minus the pressure below the plane surface, or in other words, there is the pressure difference between the curved convex surface and the plane surface. All right, so now what happens that before the change, that means before the surface was made convex, the system was in equilibrium, at equilibrium, and after the surface has been made convex, the system again gained equilibrium. So now from one equilibrium situation to to attain one equilibrium situation to another equilibrium situation. So okay, so that means from going left to right, certain condition has to be fulfilled, otherwise it won't happen. And that condition required is basically when we have this change, that means delta mu vapor, means the change of the chemical potential of the vapor should be exactly equal to the change of the chemical potential of the liquid. So whenever this condition is satisfied, that is delta mu vapor is equal to delta mu liquid, then only we have both the equilibrium conditions satisfied before and after the change. So if that is the case, then what would happen? You see that now we can simply write the equation as, so whatever delta mu vapor is RT ln P divided by P naught is equal to delta mu liquid, which is molar volume multiplied by the pressure difference. All right. So now you see immediately we get an equation, and this equation is nothing but the Kelvin equation for the pressure difference at the curved surface. Okay. So once again, P is the pressure, vapor pressure above the curved surface, because we have made it convex surface, so we can also call the convex surface. And P0 is the pressure at the plane surface, okay, or the vapor pressure above the plane surface, same thing, is equal to molar volume of the liquid multiplied by delta P. So this delta P is actually the pressure difference between curved and plane surface. So next question is, can we relate this delta P with something else? Or the question is, how can we measure this delta P? So can it be expressed into some measurable quantity like surface tension or like radius of curvature or something like that? Okay, so we can also assume that if it's a convex surface, so we can assume that it's a spherical, and if this is the center of the curvature, so the radius of curvature is r. Okay, so can the delta P be related to the radius of curvature r? So I think that we should stop now at this point. So in next lecture we would try to relate this delta P with some measurable parameters. It can be the surface tension, or it could be the radius of curvature, or both. But for the time being, let's try to recognize this equation as the Kelvin equation. So in the next lecture we would go details. So we will have a complete expression of Kelvin equation, and we'll see what are the very important implications and practical applications of Kelvin equation in daily life and in colloid surface and nanosciences. Okay, so we will see you in the next lecture. Till then, goodbye.